Well, hi everyone, this is a quick run through of galvanic cells, specifically looking at how to calculate the standard potential difference. What we'll need for that is this data sheet. Now, Board of Studies, NASA, has redone the data sheet this year, and there is a whole lot of crap in here. Scary crap too. We'll do a lot of this in Year 12. So we know we always get our periodic table in an exam, and this is the page we're going to be using for our electrochem. It shows us some standard potentials. Looking at this page a little bit more closely, you can see that they're all reductions. So just by convention, we always write these things out as reductions. So every single thing on this page is gaining an electron, and every single thing on this page has also been given a voltage. So yeah, I think that's a really interesting bit of reference data. Looking at it very closely though, you can see at the top you've got your classically reactive metals, your potassiums, your calciums, your sodium, as you make your way down in group 1. And then as you head to the bottom, you have your just as reactive non-metals, everything from group 7, your halogens, so heading up group 7. So this, I guess, table of some standard reduction potentials is a little bit like an activity series, except on both sides you have the extremes. At the top,
Sorry, I can't help with that yet.
Shut up, Google. Now at the top, you've got your very reactive oxidizing metals, and at the bottom you've got your very reactive reducing nonmetals from group 7. And in the middle, you've got, I guess, a standard, and I've drawn a line through it here, and that's given an arbitrary number of 0 volts. What we'll be doing is making half cells using 2 of these half equations, and then using these voltage numbers to find the total that a cell will give us. So, coming down, this is the one I'm going to use, and you know, because I'm very color-coded, I have just written in on the left-hand side, color-coded, oxidation for red. As we go up, the desire to oxidize increases. As we go down, the desire to reduce increases. The question we're going to go with is the classic example we've been doing lately, zinc and copper. So, for a cell consisting of zinc in its ions and copper in its ions, give me a sketch, half equations, full ionic equation, and the standard cell potential. This is what we do, boys and girls. We start with a little sketch. Here's one I prepared earlier. Move that up there. Nope, too far. There we go. Zinc in its ions and copper in its ions. And now I need to figure out my half equation. So I go up. First question is, which one is oxidizing? I go to my potentials and I find zinc here is further up the page, which means it has a higher desire to oxidize. So this one here is going to be my oxidizing reaction. Color code that in red. Down the bottom here, this is my copper, so that's going to be reducing. Color code that in blue. Now what direction do I write? Well, copper is written as a reduction, so this copper accepts the electrons to become copper solid, so that goes left to right. But my oxidation needs to change direction. I need to read that from the right to left. And I'll tell you why. If I read it left to right, well, that's gaining electrons, and you know that gain of electrons is reduction. So I actually need to read it from this side, zinc going this way, and therefore it becomes an oxidation. Then I just grab my red pen and I come down the page, and I write that in under zinc. Zinc starts off as a solid, goes to a zinc 2+, gives away 2 electrons. My copper, on the other hand, which I've color-coded blue, starts off as copper 2+, aqueous, accepts 2 electrons to become copper solid. There we go. While I'm there, actually, everyone, I'm going to get the numbers too. Let's see. zinc here has a 0.76 and the copper here has 0.34. Now this is actually really important, everyone. This one here was a positive sign, so I can keep that one here. This one here is a negative sign, but I changed the direction. So that means I'm allowed to change the sign. I need to change that to a positive. So the zinc has now a positive 0.76. 0.76 volts. And the copper has 0.34. Yep, 0.34 volts. Excellent. Now, while I'm here, I'm going to finish off my sketch. So I've got the zinc in. Now that I know that it's oxidizing, this one must be reducing. And I know that anox, so that one here is my anode. Negative sign. And I know that there's a red cat, so this one here must be my cathode. I do have to write this in, have to give the symbol, good. I know that the zinc is oxidizing, giving away electrons, so the electron flow goes like this. Anox, red cat. Both of my electrodes labeled, I gotta label my salt bridge I suppose, but I'll do that afterwards. Rough sketch done. 2 half equations done. All I did was really rearrange, not even rearrange, I just reversed the direction of the zinc, brought it down, and I just copied the copper. So 2 half equations, take that one off. Now my net ionic equation, what I'm going to do here is actually just make a copy and paste that there, excellent. And now I'm just going to rearrange it. Look, I've got my zinc there, yep, and these guys can come down, and then these guys can come down. There we go. Add a plus sign in there, change that to a plus sign. There we go. And now my 2 electrons there cancel with my 2 electrons there, so I can get rid of them all. And that, boys and girls, is the easy way of bringing your 2 half equations together and getting my full equation. I can now tick that one off. And now my standard cell potential is very simple as well. I simply take this one and I add it together with this one, which is 1.10 volt. 2 significant figures. So essentially the zinc brings in 0.76 volts, the copper brings in 0.34 volts. I add them together to find the, how far apart they are, and the number that we've given that is 1.1 volts. Now for all you physics kids, that's talking about the push. So the greater the separation on this table, the greater the potential difference will be, and the higher the voltage will be. And that's actually where we get the word potential difference. It's because it's the difference in their reactivities, how much one wants to give or push the electron versus how much the other one wants to pull. So the most powerful cell that you can make here, the highest voltage cell, would be as if you took this one here with this one here, because that would have the greatest potential difference. Now, a few notes on that potential difference. It's under standard temperature and pressure, so all of this data is really high quality conditions. That's why ours will usually suck when we do it in the lab and compare it to these ones, because they're under STP. And the potential difference is always positive, because a positive number means the reaction will proceed forward spontaneously. We know that these are how galvanic cells work. It happens spontaneously. So if you are doing this with pen and paper and you are getting a negative number, that means you've done something wrong, or what you've actually predicted on paper would never happen in reality because it would not be a spontaneous reaction. Look, that was pretty long. Thanks for staying with me. And